morning, people. I hope you're doing well, my lovelies. And let me show you something. Albeit with a warning, it may contain science. Previously unseen science. Well, yeah, because it's recently published, but also because it's about stuff we've recently seen. Researchers published in April's issue of Earth and Space Science the discovery of almost 20,000 new mountains. No, not mountains on some exoplanet, not mountains on the moon, on Earth. 20,000 new mountains. Now, given that competitive GeoGuessr players know every single inch of video recorded land on this planet, and also probably, geologists or whatever, how possible to have found 20,000 new mountains on our own planet? Well, because we focused mostly on the 30% of Earth's surface area. The land bit. Mountains exist in the ocean as well, where they are typically called seamounts, and they're really pretty much the same as land mounts. Isolated elevations in the seafloor with steep slopes and a little summit at the top. And like land mounts, many of them are the product of tectonic movement. Some of the tallest seamounts are so big, they actually break sea level, and indeed, the tallest mount on Earth isn't Everest at all. It's Mauna Kea, because her base is below the sea, and her dry prominence, her base to peak height, including what's below sea level, is 9,330 meters, or 30,610 feet, versus Everest's scrub 8,848 meters, or 29,032 feet. So, reconsider going to climb Everest. It'll take pressure off the mountain's infrastructure. There are other impressively tall options, is what I'm saying. Now, before this recent discovery, scientists had a total of 24,600 seamounts cataloged, meaning that this paper has almost doubled the number of known seamounts. So, what enabled us to make this kind of huge leap in seamount count? Well, I'm glad you asked, rhetorical straw man. The ocean hard nerfs our traditional planetary mapping techniques once you try to see under the water. We can't use radio telescopes, we just pick up AM talk. No one wants that. We can't see much on satellite optical due to all the particulates in the ocean. Hi, Krill. And infrared is better at picking up surface movement of the ocean than whatever the heck is going on below. Historically, that means that our primary seafloor mapping tool is sonar. The advantage of sonar is that it's very accurate. The disadvantage is everything else. To map the seafloor, you gotta put sonar on a boat and go around the whole ocean pinging as you go. It's time intensive and adds to the human noise pollution that really messes with marine animals. Our other option has literally been to shoot an airgun at the seafloor, which also creates mechanical wave whose return we can use as data about seafloor elevation. Advantage of airgun? It's a very high energy wave and even lets us map through the ocean's crust, giving us information about the composition, density, and structure below the ocean surface. Downside of airgun? It's very directed, meaning it's also a logistical nightmare mapping bits of the ocean floor one by one, but this time it's a blast of noise underwater, so we're basically doing horrible fireworks night to any animal in the vicinity when we use this technique for mapping. We've covered seafloor mapping a couple times before on May Contain Science as geologists and ocean seismologists create new techniques that are less disruptive to the animals who are just trying to climb the seabed of Mount Kea for their fishbook page, okay? One of the techniques we've covered harnessed whale song itself. You may have heard about how loud whales can be, though no, we have no evidence that they use their clicks as deadly sonic attacks. Ocean seismologists have used data from whale song as a substitute for airgun measurements, with special thanks to the whales for participation, I hope. The other alternative method we covered about 6 months ago, and this technique can be effectively described as put a GoPro on a shark. Yeah. A group of marine scientists, they put specially designed cameras onto 8 tiger sharks. Normally, I'd say someone ought to talk to the study section who approved the proposal to put cameras on sharks, but Ultimately, that project revealed 30,000 square miles of seagrass meadow in the Caribbean, and the research group at least didn't report that any grad students got eaten for trying to put a GoPro on a shark. But all of these techniques have one thing in common, and that's that they're very localized. Sonar and air guns depend on the ship's movement. Whale song and shark pro depend on, well, wherever those whales or sharks want to go. It's why, overall, we've only mapped about 20% of the ocean's floor. These techniques are all quite accurate in their own ways, but none of them are terribly conducive to getting an overview of 70% of our freaking planet. That's where this new mount mapping technique stands out. Geophysicists sure didn't find 20,000 seamounts by pinging sonar from a boat all over the ocean. Instead, they harnessed the power of gravity. Researchers used satellite altimetry, which uses radar to calculate the distance between satellite and ocean surface. It turns out that because rock is denser than water and seamounts are really big, there are actual gravitational anomalies over seamounts which pull water to them and create slight bumps in the sea level over the big underwater mountain. By measuring these gravitationally induced anomalies in satellite altimetry, we can actually get meaningful information about what's beneath the sea. Now yes, rhetorical strawman, we're all thinking it. How do ocean waves not mess with measurements that rely on teeny tiny differences in water levels? Short answer? Yes. They absolutely do. Waves and currents are one of the multiple sources of error that can come from this technique, and it's even harder when you're looking at smaller seamounts. The smaller they are, the less gravitational differential there is, the less pronounced the anomaly. The longer answer is that geophysicists have slowly been making progress in doing big maths to pierce through various sources of error and pick up on vertical gravity gradients that signal seamounts, all of which was checked against locations mapped by known accurate techniques like sonar to aid the accuracy of the model. Now, this study is the payoff to all of that mathematical refinement. That's how it is in science sometimes. Gathering data wasn't the problem, it's mathematically extracting the signal wheat from the noise chaff. Not like putting a GoPro on a shark. There, I'm pretty sure the problem was putting a GoPro on the shark. But the point is that with the data analysis locked in, our researchers were able to look worldwide, letting confirm and correct existing datasets as well as identify these 19,325 new seamounts, many of them the small kind that would have been virtually undetectable to previous surveys. Now, don't worry, there's definitely still a place for GoPro on a shark, whale sonar, and other techniques, even with the power of gravity god and anime on our side. This study's technique gave us planetary scales of data at the price of lower levels of certainty. Gravitational anomalies are circumstantial evidence, if you will, versus smaller scale but more accurate techniques like sonar, the sound wave don't lie, or shark pro, because if a camera sees seagrass, it means there's seagrass. Gravitational anomalies are cool and shockingly useful for finding huge underwater topographical features like seamounts, but we never could have used it to find a seagrass meadow. That doesn't affect gravity the same way. This technique is another tool in ocean geologists' toolbox, offering different benefits and drawbacks than existing approaches. And yet, this situational, circumstantial tool is still incredibly valuable. We now know so much more about hot seamounts in our area, and that's important for a couple reasons. One, even these smaller seamounts can still be dangerous, as some of them do get up to the height a submarine can hit them. And, they have. Just ask the USS Connecticut from its repair yard in Washington State. But they're also just very cool on their own. Just as land mounts develop rain shadows as air currents move up and around them, water movement around seamounts mixes up nutrients and, in combination with the cracks and crevices of the mount itself, make these locations excellent hotspots for marine biodiversity. That means we could have almost 20,000 places to look for little ecosystems. But before we get ahead of ourselves, we have 20,000 new mountains, so first things first. Who wants to be the first to name one?